Well, hello again. We're going to talk about Pascal's principle and then follow that with Archimedes' principle today. So Pascal's principle says the pressure applied to an enclosed fluid, so the fluid has to be enclosed in something, is transmitted undiminished to every point in the fluid and to the walls of the container. And so the easiest way to introduce this that most people have found is the idea of a hydraulic lift. So here I've drawn a hydraulic lift. I've got an area here of a piston. So this is a piston. If you're not used to thinking of a piston, think of it as like the plunger in a syringe. This can move up and down. Here's another larger piston that can move up and down. And inside these pipes, I've got a fluid, and this pipe is bigger than this pipe, and they're connected with a pipe here. So what I'm going to do is I'm going to apply a force over here, some force F1 that will increase the pressure over here, and that will lead to some force F2 over here, and I want to use Archimedes' principle to calculate what this force will be over here. What I know is when I apply this force here where there's this area A1 is the increase in pressure will be the same everywhere. So the pressure increase over there, delta P1, is the same as the pressure increase over here, delta P2. So the pressure increase over here, when I push down on this plunger here, on this piston, that pressure increase is the force I apply over the area. That's the definition of pressure. That pressure gets transmitted everywhere in here, that pressure increase. That's what Pascal's principle says. And so that pressure increase will be F2 over A2 over here. That pressure gets applied everywhere, this larger piston. And this is, for this example, my statement of Pascal's principle. Now the principle is more general than that. This is it being applied to a hydraulic lift. So I've got an example here for you. Suppose this piston over here has a diameter D1. I did this in inches and pounds to make it easy to think about, of a ½ inch. So a little thing about the size of this marker. And let's suppose over here, this is about the size I've got it drawn. D2 is about 6 inches. So this would be about the size if you've ever seen one of these lifts lifting a car up in a shop. And let's suppose I apply a force here, F1 of 10 pounds, and I want to see what force do I get out over here. Well, the force F2 will be F1 times the ratio of these areas, A2 over A1. So I need to compute these areas. So A1 is just pi D1 over 2 squared, D1 over 2 because it's pi r squared. That's pi times 0.5 inches over 2 squared, and that is 0.96 inches. The area over here, A2, brute, is pi times 3 inches squared, excuse me, is 9.42 inches. So this tells me that my force is 10 pounds. The 10 pounds I apply times 9.42 square inches over 0.196 inches squared. This should have been inches squared. So my output force I get, when I apply 10 pounds on one side, I get 480 pounds of force on the other side, just by pushing here. That's not enough to lift a car, but what I could do is I could put a lever on this, and by applying, 10 pounds out here, I could maybe get, 50 pounds or 100 pounds there of force by using a lever, and then, if I could get an even larger force here. So just by using Pascal's principle, I've multiplied this force considerably. And that's how hydraulic lifts work. and how all of the hydraulics on large pieces of machinery you pass on the highway, they work that way. So that's Pascal's principle. All right. Next, we need to talk about Archimedes' principle. Archimedes' principle has to do with something called the buoying force or the buoyant force. This is the force you feel holding you up when you're in water. So when you're in water, you feel like you're kind of floating a little bit. That's due to the buoyant force, and the size of that force is described by something called Archimedes' principle. So Archimedes' principle says the buoyant force is equal to the weight of the displaced fluid. What do I mean by that? I mean, if I've got some fluid here and I put something in that fluid, some object, and say part of that object is underwater, part of it's not, so there's this V submerged here, so part of this object is underwater, part of it is not. The weight of the part that's underwater, the weight of the part that displaced the fluid, that pushed the fluid out of the way. That's what I mean by displaced fluid. There was water there, and then when I stuck this barrel or whatever it is in the water, it had to push water aside for it to be in the water. That's what the displaced fluid means. The weight of the fluid that got pushed aside, that weight is the size of the force that helps hold this up. And we call that the buoying force or the buoyant force, FB. Well, how big, that's the force you feel holding you up in the swimming pool that makes you feel like you weigh less. So how big is that? Okay, well the volume of the fluid displaced is V submerged. That's what I'm calling submerged. I could call it displaced, I guess most people call it sub for submerged. We know that buoyant force is mg, where this is the mass of the submerged fluid, but we know that density is mass over volume, so the mass of the submerged fluid is its density times its volume. So the buoying force will be the density of the fluid times the volume that's submerged of the object times g. See, because rho times v is just m, so this is just mg, just like you're used to thinking. That's mg, but it's the mg of the fluid that got pushed aside. Usually water, but not always. It could be some other fluid. So this buoying force is density of the fluid, remember it's the fluid, volume submerged g. Now if the entire object is submerged, we'll do an example like that, then that volume is the volume of the whole object. If only part of it is submerged, then it's just the part that's underwater, or the part that's under whatever fluid you're dealing with. So let's do an example here. Let's do an example like I've got here. Let's suppose 80% of an object is below seawater. With density 1.025 grams per cubic centimeter. That's the density of the seawater, the density of the fluid, not the object. What I want to know is what is the density of the object? All right, well let me start with something I know. And I'm assuming the object is floating because only 80% of it's below, so 20% of it's above. So here's my object as I have shown here. There's a buoyant force holding it up, a buoyant force. It still has weight down, mg, but this is now m of the object. When I did this stuff a while ago, this was m of the fluid. So if this thing is floating, whatever this object is, if it's floating, apparently this mg of the object and this buoying force are equal. That's why it's floating. The buoyant force is holding it up. The buoyant force is this: rho of the fluid, V submerged, G. The mg of the object, you say, well, I don't know how big the object is. You didn't tell me. I know. But I do know that m of the object is the density of the object times the volume of the object. That's its density, times its volume will give me its mass. So mg will be density times volume times g. So these are equal. Rho of the object, volume of the object, times g. You may have to spend a few minutes convincing yourself of this, but this is just m of the fluid, g, has to equal m of the object, g. That's all this statement is. But this is m of the fluid that got pushed aside. That's Archimedes' principle. And this is m of the object. Just mg equals mg for the thing to float. Now, the g's cancel. Volume submerged over volume object is 0.8. That's what this 80% is. So volume submerged over volume of the object is 0.8. That's what the 80% is below means. And that is rho of the object over rho of the fluid. That's just algebra. Convince yourself I did the algebra right. So you'll probably have to practice this. So we can solve this for rho of the object. Rho of the object is then 0.8 rho of the fluid, which is 0.8, 1.025 grams per cubic centimeter. That's a typical density of seawater. Seawater density varies depending on where you are. It's typical. So that's 0.820 grams per cubic centimeter. And we never had to know actually how big the object was. We just had to know how much of it was below the surface. Notice a corollary of this is something can float only if its density is less than the density of the liquid. If its density is greater than the density of the liquid, then the V submerged over V object, rho object over rho fluid, this won't work. Then it will sink. If the density is greater than the density of the liquid, the object it will sink. Well, one more example, and then you can, of course, practice this in your homework, like always. So I'm going to do an example of when something does sink, when the entire object is below the surface. So I've got water here, and I've got a sphere. That's supposed to be a sphere. And it's an iron sphere where the density of iron is 7.874 grams per cubic centimeter. And what I want to know is, what is the acceleration of this sphere underwater? See, I do have to know how big it is, so what I give its radius? I let it have a 5 centimeter radius. I want to use F equals MA, and I'm assuming no drag force. So if you've studied drag in lab, we didn't do it in my class. If you've studied drag in lab, I'm assuming no drag from the liquid. My forces are F buoyant up and mg of the object down. So I know F buoyant up minus mg down is MA. So I need F buoyant, mg, and MA. F buoyant is rho of the fluid, volume displaced or volume submerged, G. But now the entire thing is submerged. So the volume submerged is the entire volume. Mass of the object is rho of the object times volume of the object. So we can solve all these. The volume of a sphere, because I need that, you might not remember, is 4/3 pi r cubed. And I've done that. You can practice that to make sure you get that right. Let me see if I can find it here. That turns out to be 6.545 times 10 to the minus 5 cubic meters. You have to do it in meters. This makes the buoyant force, rho of the fluid, 1,000 kilograms per cubic meter. If this is fresh water, I did seawater for the other one, this is fresh water. V submerged is 6.545 times 10 to the minus 5 cubic meters. G is 9.8 meters per second squared. That gives me a buoyant force of 0.64 newtons. M is rho of the object, V. Rho of the object is 7,874 kilograms per cubic meter times V, 6.545 times 10 to the minus 5 cubic meters. That gives me 0.515 kilograms. And I'm running out of space to get this to fit on the video. But I solved this for A. A is FB minus mg over m. And notice I know all that now. I know FB is now this, 0.64 newtons. M is 0.545 kilograms times 9.8 meters per second squared over 0.545 kilograms. And assuming I keyed all that in right, I certainly hope I did, that gives me minus 8.56 meters per second squared. All right. So two examples, one, the one before, something floating, this one, something sinking. They are kind of subtly different, even though the principle is the same. So be sure that you work through them both and you really think about why you're doing each step. Because Archimedes' principle seems pretty straightforward, but it actually it takes a lot of thinking to make sure you understand, you really understand each part. What am I doing? Why is it that density? Why is it that volume and not that other volume? Why is it that density and not that other density? So think about it. Don't memorize how to do it. Memorization of how to do it is not really learning. Think about how to do it. All right, I'll see you soon.